Alright, today we begin Chapter 8, which is titled Sequences, Series, and Probability. So today we're going to be talking about introducing sequences and series, and we'll stick with those for a little bit. Towards the end of the chapter, we're going to start getting into probability. So first we'll talk about an infinite sequence, and later we'll talk about how that differs from a series. A sequence is essentially a fancy word for a pattern. And in math, what we do is the sequence is we call the first term A1, we call the second term A2, A3, A4. So if I talked about A7, that would be the seventh term in whatever pattern you're describing. And n can go up for as long as it can go all the way to infinity. Sometimes it's specified saying A only works from numbers greater than 2 to numbers less than 10. It's all relative. It depends on the problem. But they tell you, sometimes they give you a restriction on n, and that's the idea of telling you, to tell you a little bit about it. When you come up, eventually you can come up with kind of like formulas to determine what the nth term is in a pattern, and you'll see that later today. So it is possible for n to go on to infinity. In those times where n does not go on to infinity, n is only valid from 1 to 10, that would be considered a finite because it's countable. It would only work if n is 1 all the way, or 2 or 3 all the way up to 10. And eventually it comes to a point where it stops. So even if you went a finite series even from 1 to a million, that's countable. So that would be a finite sequence as opposed to 1 to infinity, which would go on forever. So the first four terms, what we have here is this is essentially our definition, an. It gives us a way to figure out a1. It's like a formula. All I have to do is substitute in 3 times 1 minus 2, so a1 would be 1. a2 would be 3 times 2 minus 2, so 6 minus 2 would be 4. Now I'll let you check your work for the next ones. a3 is 7, a4 is 10, and a5 is 13. And if you notice and you look at these numbers, I would hope you come up with a way to justify that pattern. And that pattern here is that it starts at 1 and it continues to go up 3 every single time. Now, this is a mathematical way to describe that pattern. All right, so here's, I should call it a sequence. All right, so here, again, same idea, first 5 terms. So a1 would be negative 1 to the first over 2 times 1 minus 1. So negative 1 to the first is negative 1 over 1, so that would be negative 1. a2 works the same way, negative 1 squared over 2 times 2 minus 1, so that would be 1 over 3. a3, negative 1 cubed over 2 times 3 minus 1, so that's going to be negative 1 over 5. a4, you can do it in your head, that's going to be 1 over 7, and here a5 is going to be negative 1 over 9. So if you notice here, the bottom of that fraction is consistently getting bigger by 2, and in every term the sign is changing, so it's going positive, negative, positive, negative. That can happen in a sequence. So there's kind of 2 parts to this sequence that define its pattern. All right. Now, here we're going to do exactly the work backwards. Is I've given you the pattern, and you need to come up with I've given you the numbers, the sequence, and I want you to come up with what the statement looks like. So an, I want a definition for this. Well, I know that my first term needs to be n. I'm sorry, I know that my first term, needs to be 1. So when I substitute 1 into this, I need to get an answer of 1. So this becomes a little tricky because a lot of people say, oh, it's going up by 2, so that needs to be in here. So there's 2n. Now the problem is, if I do plus 1, this does not match up. If I tried to substitute 2 times 1 plus 1, this would actually be 3. So this here is actually getting me the second term. All right? This will be my calculation for a2. So this formula is not quite working for our series, so you have to it's a little bit of guess and check. 2 times n, if I then say, well, minus 1, that would work a little bit better, because now if I try a1, it's 2 times 1 minus 1, ends up being 2 minus 1, which is 1. That is the first term in my sequence, and if I try a2, a3, a4, they will all work. So sometimes I realize that the 2 is in the problem because every term is going up by 2. I realize that pattern. It's always going up by 2. That's why this multiplication by 2 is in the problem. And then it's really a little bit of guess and check to get the second number to work. So if you're thinking that looks a little bit like a slope, I can see a little bit of a relationship to that. Okay, so Fibonacci sequence, you may or may not have heard of this before. The word that I'm really concerned with here is defined recursively. All right, the Fibonacci sequence is defined, it's a sequence, meaning it's defined recursively. And what it means to be defined recursively is to be able to get the 7th term, you need to know the 6th term. Or to be able to get the 15th term, you need to know the 14th term. You need to know the term before it to be able to get the next term. And without the term before it, you can't get the next one. So if I gave you the 5th term in the Fibonacci sequence, but you need the 10th, well, your sequence is going to have to go, well, I need to get the 5th, then the 6th, then the 7th, then the 8th, then the 9th, and then you can finally get to the 10th, or whatever number you so desire. So this is the actual definition for the Fibonacci sequence. I'm not so concerned that you remember the definition for the Fibonacci sequence. What I am concerned with is that you could see something defined recursively and be able to list the terms out. Right? So now they've given you A0 and A1, and I essentially want to know the first 5 terms. So I know the first 2. The first 2 are 1 and 1. But now I need to be able to get the next term, which after A0 and A1 is going to be A2. All right, to get A2, I would need to do A2 minus 2, so that's really A0, plus A, and that's going to be 2 minus 1, so this really here would be A1. So to do that, I would need to do A0 plus A1 to get A2. So that would be 1 plus 1. The third term in the Fibonacci sequence would be 1 plus 1, which is 2. To get A3, I would need to do A1 plus A2. And so A1, remember here's A0, A1, A2. I would need to add up 1 plus 2 and end up with 3. So sorry, write this a little better. To get the A4, I would need to do A2 plus A3, and that would be 2 plus 3, which is 5. And now you're starting to notice a pattern. As I start to write this sequence out, you're noticing, oh, you're adding these two and you're writing the next number. If you had to go further, the next term in the Fibonacci sequence is 8, because 3 plus 5 gets you 8, and then 5 plus 8 gets you 13. And you see the Fibonacci sequence grows pretty quickly. 5 plus 13 gets you 21. And if I asked you for the 15th term, there's no formula to get the 15th term. You would need to literally go out and continue this pattern until you get to the 15th number. All right, so here's a little more practice with recursive. All right, here's just another way of defining it. What I've given you is I've given you A1, and I am asking for the first 5 terms. So the first term is 15. That's given. In this recursively defined sequence, to get A2, I must do A1 plus 3. Right? That's essentially what this is saying. Well, I know A1, they told me that this is 15, so that means A2 is going to be 18. To get A3, I need to do A2 plus 3. So I know A2, I just found that out, that's 18. My next value is 21. To get A4, again, I need to use A3 to get A4, because it's A3 plus 3. Now, some sequences can be written both recursively and using like a formula, which we stated before. So you could actually see this formula. You could this whole sequence. You're saying, oh, that's a pattern of going up by 3. Yeah, this could have also been written as 3n plus 12. Now, this sequence and this sequence are identical. They're just defined 2 different ways. So we do need to know both, because you will see both recursively defined and using more of a formula. All right, so factorials. Factorials are in here because we are going to see probability this chapter, and you're actually going to see it very shortly, even I think next section. I'm sure you've seen a factorial before. 7 factorial is just 1 times 2 times 3 times 4 times 5 times 6 times 7. So it's all the first 7 integers multiplied together. That's what a factorial is. And let's see. It's multiplication. So the only part to factorials that you need to pay attention to is there's a special case, 0 factorial. 0 factorial is equal to 1. And if you have questions on that, I will show you. If you think about, 1 factorial, I assume, I'll answer why this is in a second. But first, let's answer these 5 questions. So that's just 1. Here it would be 1 times 2, which is 2. 1 times 2 times 3, which is 6. 1 times 2 times 3 times 4, which is 24. And 1 times 2 times 3 times 4 times 5, which is 120. So my question is, if you're wondering why 0 factorial is 1, well, if you think, what's the pattern going backwards? Right? And if you think, here I divided by 5, here I divided by 4, here I divided by 3, here I divided by 2. To get to 0 factorial, I'm going to divide by 1, and that's why 1 divided by 1, that's why that answer is 0 factorial is 1. So here's a little more practice with the sequence. Looking at our first 5 terms, we're going to do A1, A2, A3, A4, and A5. So that's going to be 2 to the first over 1 factorial, which is just 2 over 1. So we'll call that 2. Here you're going to have 2 squared over 2 factorial. That's 4 over 2. So that's also 2. A3. 2 to the third over 3 factorial. So you're going to have 8 over, that's going to be 6. So it's going to be 4 thirds. A4, 2 to the fourth over 4 factorial. So that's going to be 16 over 24. That's going to be 2 thirds. And last, the 5th term here, 2 to the 5th over, that's what do we say, 120. That's going to be 32. Over 120, so what's that reduced to? 16 over 60. We can do 8 over 30. We can go one further. We can go 4 over 15. So that would reduce to. So there's your first 5 terms. No calculator needed. Nice part about simplifying factorials. So if you think of this 8 factorial as 8 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. On the bottom here you have 2 times 1, that's 2 factorial, and then 6 times 5 times 4 times 3 times 2 times 1. The nice part is, if you think of these as fractions, 6 times 5 times 4 times 3 times 2 times 1 is on the bottom and also on the top, so they all cancel out. And here, obviously I don't really need to worry about multiplying by 1, that doesn't change anything. 2 goes into 8 4 times. So my answer here is 4 times 7, 28. Not a whole lot of work needed. If I'm looking here at my second problem, I think of this as 2 times 1, times 6, times 5, times 4, times 3, times 2, times 1, over 3 times 2, times 1, times 5, times 4, times 3, times 2, times 1. And I look, all right, 5 times 4 times 3 times 2 times 1 is on the top and the bottom. Here's a 2 and a 1 on the top and the bottom, and this simplifies down to 6 over 3, which is really just 2. All right? Probably couldn't put it into a calculator that fast. So the question is, n factorial over n minus 1 factorial. So if I thought of that as 9 factorial over 8 factorial, or if I thought of it as 6 factorial over 5 factorial, 6 factorial over 5 factorial, right? What's going to happen here? Essentially, this 8 factorial is going to cancel out. 9 is going to stay, but everything after is going to get canceled out. This answer would just be 9. This answer would just be 6. So what's the formula for this? Is that it really breaks down to just n. We will pick up summation notation on the next video.